Today we have two amazing keynotes for you. So the first keynote will be given online by Dr. Baishakhi Ray. So Dr. Ray is an associate professor at Columbia University in New York. Her research interests are in the intersection of software engineering and machine learning, and she has received prestigious awards like the IEEE TCSE Rising Star Award and the NSF Career Award. And her research has won several distinguished paper awards. So please join me in welcoming Dr. Ray. You should not.
Hello.
Hello, Dr. Ray.
Hi, can you hear me well?
Yes, I can hear you very well. Awesome. So I just gave her...
From my side, I hear an echo.
I think she cannot hear us.
I can...
Is it going okay now?
Yes, yeah, I can hear you very well.
Yeah, it's better now?
Yeah.
Perfect. Thank you very, very much. So I just introduced you. We still see the camera now. Yeah, we see your screen now.
Okay, great. Yeah.
Okay, thank you. So please join me in welcoming Dr. Ray. Please
Shall
go
I
ahead,
start?
Dr. Ray. Yeah, please go ahead.
Hello, good morning, everyone. So I am Baishakhi Ray, and thanks for attending the talks super early in the morning. So anyway, hope I can tell you something interesting. So today I am going to talk about towards code-aware code models. You know, in today's world, software is almost everywhere. We use software from the time when we wake up throughout the day in different aspects of our life, and then till we go to sleep, or even probably during our sleep also. And to support this humongous growth of software, developers are constantly working towards producing code. So not only they are working on coding, they also want to have good quality code. So they are testing that code. If they find problems in that code, they are debugging. Then they try to fix those problems. And finally, they have to also write documentations to explain what they are doing for better readability, maintenance, and all. So in my research agenda overall, I want to improve all these whole software development ecosystems through smart techniques, and AI is part of it. So the big question is that then how to improve these whole different jobs of software development. So one big aspect is how to improve developers' productivity. That means, not only they can churn more and more code, but it also involves their well-being, right? How to help them doing their job and improve the whole overall software development experience. Similarly, I mean, while we have to think about the increasing productivity, we have to also think about how to improve software quality so that that software is better reliable, secure, performance efficient, and whatnot. So this has a huge, we have a huge expectation then from both the developers as well as the software. So the whole software ecosystem. So while the field of software engineering is trying to work on this problem for a long time, say a decade ago, suddenly there was, the GitHub and large amount of software data came into the picture, as well as the large amount of computation power. So with the availability of software data and computation power, now people started talking about whether we can smartly analyze these big software data to improve the whole software development ecosystem. So if we look back, not very long past, a little bit, maybe a decade or so, people started observing the repeatability or statistical predictability of the code somewhere around 2012, 2014. So this observation created a big opportunity of today's AI-based code model that yes, because of this repeatability, we can do something more smart uh, by leveraging the statistical nature of the code. So after that, follow a lot of like this old school kind of applying statistical model like RNN, first n-gram, then LSTM, then RNN, and they showed improvement from their immediate predecessor. But then somewhere around 2020, there was a big shift in the technology, especially from the AI side, where the transformer-based model came into the picture. And we, from our community, we started, I mean, from in both industry and academia, we started building these transformer-based models specific for code. And they again showed decent promise in different software engineering tasks. And where we are now we are moving towards more larger and larger models. They are pre-trained with lot of data, including text, code, and many other modalities. So most of you probably heard the name of like Code Llama, GPTs, Star Coder. They are more like new generation models. They usually have huge number of parameters. And recently, at least towards the beginning of this year, we started hearing about AI engineers. So now not only individual tasks, this entire ecosystem that I showed you, the development ecosystem, several multiple AI agents can solve the entire ecosystems of software development. So if I compare it like human history, so slowly, as you can see the figure in the corner, slowly the AI is becoming more and more mature. Their brain power, that means their intelligence power, we will see whether they're intelligent enough, but somehow their capability is increasing. So if we focus on today's model, so there, especially the GPT, Code Llama, Star Coder kind of big model, as well as the multiple multi-agent system, we will see there are three main techniques that are going on to make the software ecosystems, software engineering ecosystems better. So first, we are trying to make the models fundamentally better with many things, like we probably are increasing the size, changing the parameters, slightly changing their the loss functions, and etc. etc. Then another main thing was going on is the prompting. So whether we can do chain of thought kind of prompting or some other smart, like showing some example in context learning to improve to leverage the power of these large models. And finally, again, very recent progress is that now for different kind of jobs, if we have AI agents, whether through chat or other kind of interactions, we can achieve much more complex jobs. So we can see the promise in real real tool. So for example, GitHub Copilot, Amazon Whisperer, ChatGPT, they are all real products which help us to develop code. We can see many of us use this kind of ID, and they are not limited to only code generation. We can also sometimes predict bugs and generate test cases and things like that. And companies like, say, Google last year actually said that 3% of their code is now generated by AIs. There are huge academic papers are coming up using this kind of AI-based model. So with all these super exciting news, I would like to pause and ask this question, whether these AI-based agents are really understanding code, or whether they are seeing lot and lot of data and then making some prediction for easy task they are working, which is good, but what they are actually learning in terms of code. So to answer that question, we did some experiments. So for example, there was a code we asked encoder 6B model, which was last year. When we performed these experiments, it was a pretty big model. So we asked it write a Python function to determine whether all the numbers are different from each other. And we basically semantically paraphrased it and said, write a Python function to see if all numbers differ from each other. So they are semantically same, but see the code generated by the LLM, they are basically generating completely opposite code. The left-hand side is equal to, while the right-hand side is not equal to. So basically completely reverse meaning in this context. So definitely, I mean, there is some problem. Not only that, here there is another model from Salesforce CodeGen, a very popular model. There, if we just change a function name, it was remove underscore lowercase in the original prompt, and we just changed it to the camel case, the code completions completely changed, and the behavior changed. So something is definitely going not right. And then this is our latest endeavor to check GPTs, because previously it was a kind of smallerish model in today's standard. So these experiments with this on GPT and GPT 3.5 and 4. So we take some natural language that instructs the GPTs to write the code, and then take the code and ask GPT again to summarize that code, like what it is doing. And then take that summarized code, which is NL1, and ask the GPT again to generate the code. So in this chain, like we give natural language, then generate the code, which is PL, then PL to NL, then NL to PL. If we do this kind of chain, but the same concept, GPT should be able to do the same thing again and again, we see that GPTs do not perform very well. And not only GPT, not the other models are even poorer. So we see GPT-4 has in this kind of setting up to 14-15% percentage drop. In human eval plus data, it's a kind of code contest kind of data where you ask the model, give some natural language, the typical interview questions that you might face, and ask the model to generate the code. And so GPT-4 fails, GPT 3.5 fails, even, the failure rate is worse, like around 43%, and all the other models are even worse, like Code Llama fails up to like 73%. So here we can see the LLMs severely lack consistency. So they basically do not even understand the code and its summary written by themselves, because in this whole chain, the code, after the initial prompt, the entire chain is written by the LLMs themselves. So they should have some understanding, and they are failing. So, so that means something is definitely going very wrong. And one of the hypotheses I have, that the majority of LLMs are treating code as text. So, for example, another thing, we saw, if you just treat this code as a text, they apparently look very, very similar, with this certain difference that the variables have different type. And because of this subtle difference that they have that float versus integer type, the right-hand side was actually has the integer overflow vulnerability. So definitely, I mean, treating code just as a text is not good enough if you care about the quality of the code produced by these models. So what the mainstream interest is right now going towards big. So big model, go big parameters, lot of data. However, what we need basically, good model, good data, and then making the model more smart rather than big. So to make a code-specific model smarter, we need to understand different properties of code. So code has first lexical properties, and these are basically variable names, keywords, and the current models are quite good at understanding this. So here we did very well. However, code goes beyond that, right? Code has structure, code has semantics, like code takes some input and gives some output. Code can be represented as graph. So if you say take a natural language and say this is an example where I say that I saw a man on a hill with a telescope. So this English text has some ambiguity, right? If I tell you this text, which is a perfectly grammatically correct text, you don't know whether I mean, did you use a telescope to see someone on the hill, or did you see someone on the hill holding a telescope? But still, this is a reasonably good sentence. However, code cannot tolerate this kind of ambiguity. So while x less than 0, this code is very different from if I just change the token x less than equal to 0. In contrast, the right-hand side code, like while z less than 0, whose 2 plus z is exactly similar to the original code. So what I mean to say that if we just focus on token, token, and token, we are missing the whole semantic properties of these models, which are very, very important for generating good quality code. On top of that, even more going deeper, code has semantics. So if I take these two instructions, they don't look similar, look different. Instructions are different. They look similar. They look different, and the model says they are not similar. However, they are basically similar because the first instruction move ex plus 0 is setting the register ex value to 0, and then the add instruction is adding 0x16. The next one is again subtracting minus 16. So they are giving similar things. So code should be exposed with this kind of input-output behavior. On top of that, code is really multimodal. So code has comments, bug reports, configuration, so a lot of textual and structural metadata. And finally, it has other diverse artifacts, like you can take a source code and represent it in binary form, execution trace. It has a lot of evolutionary data, like how that software evolved. So this is at a high level, the code software ecosystems look like, with all these different modalities and the properties of code and software. And to build a smart code, like software-based models, we have to consider all of them to build this smart ecosystem. So in my goal is to how to make this foundation model plus software engineering smarter by leveraging lots and lots of code properties. So we are doing a lot of work in this agenda. But in today's talk, I would briefly cover a very simple technique, I would say, where how using just prompting, because I feel most of us use prompting sometimes or other, but how to use code-aware prompting, we can do the unit test case generation better. So a little bit background, what I mean by unit test case generation, those who don't know. So first, we have a method, a function, which is written here as a focal method. And a good test first wants to write some test cases that can test different properties of this focal method. So for example, if I want to test this is instance value string, I would give this method input string and check if it is an instance of string, the value will be returned. Similarly, for the another path, if the instant is like date time, the timestamp would be returned. And then the third is if not string, not date time, then some exception will be returned. So this is the expectation of testing, and a good test should first call the method properly and then write all these test cases that test the different functionalities or paths that is embedded in this code. So our traditional technique, which is commonly known as search-based software testing, they do pretty well in solving this problem. So they first generate tests by executing randomly the method, and then mutate at different test case generation or the program using mutation testing to try to cover different branches, and they are very successful. There are many many test case generation tools like Penguin, EvoSuite, etc. So again, this is an example of what EvoSuite will generate. So for the covering this path, it will generate a string 0, then a timestamp because it takes the timestamp, and then call this serialize method and then check whether the return value is string 0. So it has been seen empirically that there are still certain branches in the program where this kind of search-based methods have very hard to reach because probably the branch condition is very difficult. It depends on some particular values, and they are not very good at reaching those branches. So people then started using large language model to solve that problem. And with large language model, here is the problem formulation. We have first the context, the libraries that need to be included. Then we have the class. So you ask the LLM that I want to test this focal method. This is my test context. And then this is my test from that def test, timestamp field serialize, call this function under this timestamp field class. And they also showed some success. And finally, there was some hybrid method that was proposed where they basically say that, oh, okay, this method is not covered by my traditional technique. So now check LLM whether they can improve this hybrid method. And then they show that this hybrid method has a lot of potential of improving the traditional technique with LLM. So when we tried to replicate this LLM-based approach, what we found that there are only 16% of the test cases that are generated test cases are usually fail. Their pass rate is only 16%. The test coverage also is partial. It has like 41% kind of line coverage. And we found that, they fail for many reasons, but if we categorize it, there are three main categories of failure. So first is There are misuse error. That means focal method is not called properly, so that method is not even executed. There are some missing libraries or external dependencies in the test context. And then there are a lot of paths where there were no test cases generated, so these paths are uncovered. So then from this empirical knowledge, we created the prompt so that these problems can be taken care of. So first, adaptive focal context. So only we include the relevant definition and imports that are related to the focal method. So again, the context has some limitation, right? We cannot give huge number of context because of the window length. So that's why we smartly selected the context that is related to the focal method. So this helps to reduce the focal method misuse errors. Then we have this adaptive text context where we include additional relevant, say, type or the declaration definition that is required for the creating the test cases, which reduce the undefined object errors. And finally, we use symbolic path prompt kind of a technique, which I will describe in detail soon, to increase the test coverage. So let's focus on 3 because I think that is the main contribution. So again, the challenge here, reiterating that focal method may have many paths, but only some are tested, and we want to increase the path coverage. And our insight is that multi-stage reasoning prompts allow models to solve complex problems. So step by step, try to solve the problem. So with that, we try to give the model more reasoning in terms of symbolic logic. So what we did, we prompt the model to test specific paths than the whole focal method. So first, say we ask the model to test the timestamp serialized value where the first branch is covered, like where instance value string equal to true and the returns is value. So those who know symbolic logic, this is basically the natural language, writing the symbolic logic in a more natural language way so that the GPTs or the LLMs understand it in a better way. So once this this path is taken care of, we went to the next path and similarly used the symbolic logic to generate the prompt. And then we went to the other path. So we did it by parsing the ASTs. So first value, we parsed one path in the AST, the second prompt, the second AST path, and the third one, and so on. So one problem we faced while in this approach, that say if a path has condition 1, 2, 3, the second path is negating the condition and the so on. So there is a basically blow up if we try to take care of all conditions and their negating condition. However, for testing, we basically don't need that. What we need, these minimal values that can cover all the potential conditions and not conditions, but not their combination. So with that, we linearize the branch constraints when adding the paths. And that's why it becomes almost all linearly independent paths. With if there is n branches, there are n paths that we can cover. So with that, here is our final result. So if we have a GPT-4 baseline, you can see like its pass rate is around 14% and line coverage is 36%, while our best approach, which covers all these 3 prompts, it can reach up to 2x branch coverage than vanilla GPT-4, and the test pass rate is more than 3x. So this kind of, again, by leveraging very simple software, most of us who does software engineering, software testing, are very well aware of this symbolic logic-driven test generation. We just in the prompt expose that, and that helps to improve the test generation with significant proportion. And so this shows that smart code aware properties help. So what is the where we are going from here? Again, we all know that this AI-based software engineering is the future. We now just cannot ignore it. But there is this trust issue, whether we can trust this code or trust whatever they are generating, because we don't know, we don't trust. And there are many user studies with the developers said that developers do not trust this generated code. They want more maybe test case, maybe verification, or maybe some way of increasing the trust. So if we again look back, there were traditional approach of formal analysis that gives a lot of guarantee, but they are noise intolerant, they do not scale. And where another extreme is that only probabilistic models like GPTs and llamas and all these models that we know, they are scalable, transferable, but do not come with any guarantee. So I think a good approach will be how to combine both and meet somewhere in this middle zone. We can, of course, I showed you, and my main research is how to use formal analysis and probabilistic models. But other way, we can also think about like taking developers' feedback, use explainability and all these things. And with all these different way, we can build a much smarter software engineering ecosystem. So with that, I would love to thank my students, collaborators, mentors. And also I actively collaborate with many industries, including AWS. I am part of them. The work actually I presented, the test generation is part of, I did with AWS and NSF and all. And yeah, I am ready to take any question.
So thank you very much, Dr. Ray. It was a very interesting presentation.